This content is brought to you by BEC Financial Technologies, developing and operating IT for Danish banks.
Please welcome Krystian.
Thank you very much. Hello, everyone. Today, this presentation will be a little bit different. This is not exactly pattern how basically we should use the concurrency, but what the traps came from the concurrency. A few words about me. I'm the principal Java engineer in my company. Basically, I'm working for the client, so basically I'm the consultant, which basically is jumping between the projects. Mostly of my career is related with the performance of the JVM. So I'm basically boring the person. Yeah, so a couple of years ago, Phil Carton said to us that we have two very hard things to in our industry. So basically, invalidation invalidation of the cache and naming convention of the all of the things what we're basically making in our software. But the real problem was addressed by the Herb Sutter, where the Herb Sutter basically said, okay, the free lunch is over, like before this presentation, and we need to talk about the concurrency. And okay, so basically we are talking about the Java, and everyone is aware how the concurrency works. But the real problem is a little bit different, because where we want to resolve such of the problems basically with the performance, the first unit where we're thinking about it is the threading. So we're trying to increase the threads and so on, and we basically trying to manage somehow by increasing the threads. But I think in this year, I have some of the observation about that everyone is basically screaming for the speed of the software, because the cloud is not cheap, cloud is not free. Everything what we deploy to the cloud is expensive, and mostly of time we basically don't care about the performance at the beginning of the projects. And I think the problem with that is we basically don't care about the performance at the beginning, but the performance is one of the driver of the our architecture. And where we deeply thinking about the concurrency, we need to a little bit adjust our knowledge. So 10 years ago, the software was fast, where the response time was under the 2 seconds. So currently is I didn't mention about these requirements were described by the one paper. I think that was by the Google. I'm not sure. Basically, I can say about after the presentation, and after that the P95 is the under approximately 200 millisecond. I think currently is a little bit less. I think the mostly of our services are responding, I think, under the 50 milliseconds. So that is the expectation of our customers and clients. And somehow we want to resolve such of the problems, like introducing the asynchronous APIs, frameworks, serverless, and so on. But asynchronous programming is very hard, and unfortunately, it's not easy to maintain. And where we're thinking about the concurrency, we're thinking about the splitting some of the tasks to the smaller task and try to combine with our CPU. But we need to distinguish two terms, basically the concurrency and parallelism, because where we're thinking about the concurrency, we try to hide our latency, so latency our system, and basically we can manage concurrency with the single thread, single core. I'm sorry, but where we're talking about the parallelism is basically the concept where we're using multiple cores, executing the simultaneity task on the CPU. In the best scenario, we have a separated data to process, and that basically is enough. And if we're talking about the concurrency, this is the very short explanation. So we have 2 threads. We have some of the database that might be collection, but the most the crucial part of this picture is basically contention on some of the resource. So we have a multiple unit of work like the threads, and we're trying to access some of the store. And to summarize these patterns, we can achieve that with at least one score, and issues what we can basically met in our programs is the race conditions, oversubscriptions, the thread starvation, and yeah, basically this is the popular concept. Where we're talking about the parallelism, we have many tasks at the same time. We require at least 2 cores. We reduce the total time to complete the work. And here we have different issues like the memory contentions, Amdahl law, and so on. And where we're talking about where the concurrency makes sense, we can say, okay, by default, where we have a I/O application, so or I/O processing. So basically, HTTP servers, queues, some of the FTP, and so on. And of course, we have some of the different subtasks, which, for example, like the simulation, image processing, map reduce. So basically, where we have 1,000 of the light task, we can say that, okay, there is the concurrency makes some of the good improvement for us. Of course, I assume you probably know that. So the Tomcat is I think the most popular HTTP server in the Java. So by default, Tomcat creates the 200 threads because every request is managed by the single thread. And basically, that model is very nice because it's very safe and it's very easy to understand what's going on in our programs. When we're looking on the stacked trace, it's understandable by everyone, so it's fine. But if you look on a little bit high performance servers like for example, Netty, you can find there a little bit different approach, so achieving the same or even better performance with the single thread. So basically, there is the single thread event loop, which process our request. Of course, this is the very simple setup. There is the possibility to increase that and increase the worker threads and groups and so on. But this is the very short scenario where you can achieve at least twice the better performance comparing to the Tomcat. And yeah, I mentioned about, so that is common pattern, especially for example, in the Node.js also. And you can also see that situation that potentially in your Java code. We're using some of the concept like the completable future. This is the API for the asynchronous processing, but where we don't specify the custom thread pool, and basically that heavy computation doesn't split the work to the smaller tasks. Everything will be executing in the single task, single thread. So there is nothing better. I can say that this is the very popular in the libraries because that API is a little bit basically that API hides a lot of things like the thread pools. And a couple of years ago, this project is the newest project in the Java. Try to resolve such of the problems with the concurrency, because the concurrency is problematic. I will talk about it a little bit later. And they basically want to focus on the same model like we have in the thread per core, thread per request, and try to manage somehow and tune our application. Of course, this is the concept which is already developed and provided in the Java 21, and in the Java 24 is production ready, because previously it wasn't. And of course, this is the goal, what I mentioned. So we should be very near optimal hardware utilization, very simple thread model, but this is not the case. I think what you need to remember from this presentation, that the project Loom doesn't want to change our basic concurrency model. And what I mentioned is basically boring, because potentially you know it. Of course, there's the additional laws, which can describe the scalability or unscalability of our software. And AMDAL law basically says, okay, our program can be is limited by the sequential portion of our program. So even if you have a multiple processor, but your program is still synchronous and sequential, it might be potentially slower where you increase the number of the threads. So what is the cause of the concurrency? First of all, the thread creation consumes the memory. Pretty much is the approximately 1 megabyte. So imagine a situation where you have a microservice with the 1,000 of the threads. So basically you have approximately 1 gigabyte only for the thread stacks and so on. So it's a little bit heavy to manage. Of course, the project Loom somehow resolves such of the problems, but yeah, the platform threads, the simple threads what we have before, that basically consume memory. And what I mentioned, this is by default, this is the 1 megabyte. For the scheduling is 1 millisecond. Of course, you can say, okay, 1 millisecond is not too much, so we can afford it. But anyway, if you try to, for example, using some of the pattern where you're creating and shutdowning the threads, that might be very costly. This is the OS thread. So basically, this is the thread is managed by the kernel. So every context switch basically costs us, and yeah, basically it's pretty much not under control from the point of view of the JVM. So it's a little bit mess. Where we're talking about the concurrency, no one basically think about the synchronization and the contention. So contention is the fact where we have a single source and we're trying to concurrently accessing the source, writing or reading, doesn't matter. But without the proper synchronization, we have only concurrency issues. And I think that pretty much our applications seems like this. So we have traffic lights, and that is the synchronization points. And imagine where we turn off all of the lights. So basically, this is the mess. So this is the situation where we don't control our threads and accessing to the store. The best scenario is roundabout. So basically, we're trying to somehow manage this situation by of course, proper collections, or maybe different techniques like the log-free and so on. But pretty much, this is the problem. The second problem is the context switching, where you switch between threads. Your CPU is basically crying, and tries to resolve such of the things it's problem, because if you have for example 1,000 of threads and you have only 2 cores or 1 core, the single core or 2 cores need to manage somehow. So basically it needs to stop this thread, assign the CPU time to additional to second thread, and so on and so forth. So basically this is the problem. Thread starvation. So the same problem where we have a huge executor service with which, for example, 10,000 threads, and we have only 2 cores. And imagine that every task is spending 1 second. So you can imagine that in some point of time, the thread will be stopping and waiting for the CPU. So completely mess. And of course, we have race conditions, deadlocks, merge states, hard to test, because everyone who create the concurrency software try to test it, right? Right. But I think the problem, the root cause of this situation is lack of the knowledge. So the problem is still we have a problem with the parallel streams in the collections. We're using the reactor toys like the mono from Collable without additional scheduling. Everywhere is we are using the volatile and atomic. Of course, these patterns are okay and atomics are okay, but sometimes we don't need it. And you also need to know that the volatile and atomics are expensive from some of for example, memory perspective, because we need to more barriers, or atomic access is the object, so we need to allocate. Still, we have problems with the weight in notify. So yeah, basically we have problems with the GC because every thread in the JVM has a separated space in the add-in. This is the TLAB, so the thread allocation buffer. And when the thread is allocating something, this is the particular space where which is accessible only by single thread. So it's very fast. But if you create and destroy this thread, the memory is defragmented, and you need to also know it about. Of course, this is the managed by the garbage collector, but still your application can stop. And yeah, additional, my favorite guest is basically the JIT compiler. So the JIT compiler, where we don't provide proper synchronization, JIT compiler can do anything with that code. So basically cache it, making some of the different ordering of the program. So you need to understand that from the concurrency programming perspective, we have something like the program order. So this is the order within single thread. The synchronization order says, okay, we have two or many threads, and how basically the data will be shared between these threads, and happens before relation. Potentially you heard about it. So this relation is special relation between threads when the one thread is writing something to the field, and the second can be safely reading this value from this field, because that field will be automatically synchronized. Of course, we have problems with the safe initialization and safe publication. What is that? So basically, where you're creating the object and this from this object escape. This is not from the Java memory perspective. This is not safe initialization. So it seems like when for example you have a singleton, but you share the disk of this object, potentially might be for example null value or object for example will be in the different state. Not all of the fields will be initialized and so on. So yeah. The main actor in the concurrency in the Java is Java memory model. And I think this is the hardest path in the concurrency, because no one basically read the chapter 17 from the Java specification language. And when I discuss with other engineers about it, everyone tries to run. So what is basically what is the Java memory model? So Java memory model is the set of the rules which describe what basically compiler make you do with your code about the ordering, visibility, and of course that happens before relation. But you need to be aware that without the proper synchronization, your changes cannot be visible to another thread, and compiler and CPU can reorder your instructions. So you can imagine that this is not possible, but yeah, the compiler is free to optimize your code from his perspective, but he doesn't care about the correctness of this program. Of course, from the concurrency perspective. And what I mentioned before, so this is the set of the rules which define how threads sees the shared memory, when memory is changed and is visible to another thread, and how basically the CPU and compiler can use these works for the processing. And What is more important, JVMs, basically this is not JVM, but the JIT compiler and CPU can move your instruction up and down. So basically, if you have some of the access to the field from the CPU perspective or compiler, can be much efficient where that this line will be moved upper. But from the concurrency perspective, that might be the bug because, for example, the data will be write or read in the different order. Mostly of time previously we worked with the architecture 86, and that was very strong architecture. So basically, store and load was only possible to reordering, but where you're using the Apple, you need more barriers. What does it mean? So imagine that you work, for example, in the Linux on your local machine, and you're using the old architecture 86, and you deploy to AWS, for example, on ARM. So your code might be safe on your machine, but it can be not proper synchronized on the ARM, and basically the results might be not predictable. And yeah, atomic access. Atomic access is the additional step in the concurrency, because this is basically resolved on the CPU instruction level. But you need to be aware that every place where you're putting the atomic is a cost. So of course, this is the cost from the perspective of the creation of the atomic, because this is the object. But atomic for the increasing, decreasing is fine. But where you, for example, have multiple threads and trying to summarize some of the works and using the atomics, you need to use proper object. For example, you have 10 threads and you have a atomic integer which is shared between these threads, and you want to increase this number, so everyone can say, okay, this is the compare and swap, so it's fast. But if you comparing to the order from the Java util concurrent structure, like the long adder, it's much faster because long adder was designed especially for the concurrency access, which under the hood there is the slots, and every thread is writing to these slots. There is not accessing to the single field. Word tiering. So basically, if you have a 1 byte and another byte, these bytes can be read by the CPU separately. So it doesn't mean that, for example, it might be cached or even ordered by the JIT compiler. But what is more important, if you have an array, because I think that example is more natural. So you have an array which is shared between threads. So access to the array might be atomic because we have, for example, atomic Java reference. But each element in that array is treated separately. So you can be sure that if you're accessing the whole array as an atomic, every element of this array will be also atomic. So this is not true. So from the Java memory perspective, this is the totally separated elements. And yeah, there's the additional problems like the sequential consistency program for the data-free programs. This is the basically chapter which is described. It means that if your program is data-free, it means that your program is proper synchronized. You can be sure that your program can be sequential consistency. And yeah, so basically this is this talking about the ordering of the instruction. How many times we have? Oh yeah, I need to hurry. Yeah, it's a little bit difficult where we're talking about it, but from that point of view, you need to be aware about the what I mentioned basically previously about the program order, synchronization order, and happens before, because these three of rules are more important. But if we're trying to a little bit deep dive in synchronization order and happens before, there's the distinguish between the synchronization order, synchronization order, and program order and consistency. So you see that this is very complicated. I'm totally aware that you every day remember about it where you're writing some of the concurrently. So it's fine. But if you talk reading about the happens before, this is the totally mess, because mostly of the examples is the accessing one field, which is, for example, volatile string or something like that, and everything is fine. But you need to be aware that the consistency and ordering for the happens before is totally different. And what is more important, happens before is the relation. So your program, so your access to the field might be in that relation. I will try to explain a little bit. So if you, for example, if you have a field which is volatile, and one thread is writing something, and the second is reading, you can say, okay, this is the relation happens before. But if in the middle of the execution is something different, that relation might be not met. So basically, this is the little bit hard. What is more important, if you, for example, write, first of all, you write to the volatile field, and you in the second thread, you first of all you read, this is totally okay. But for example, imagine in the thread A, you write something to the volatile field, but on the thread 2, you read this totally different field, and after that you reading the volatile field. That relation is not happens before. So basically, the simple order might be has impact on your program. And of course, we have a synchronization with an order, which is, we don't have a time to explain everything, but you need to be also aware that causality rules might be appear on the different architectures, CPU architectures. And what is more important, final fields. Final fields are treated specially in the JVM. So if you create them you create the object, you need to be aware about the how basically the data are assigned to the field. Imagine a situation. You have a constructor where you need to assign some of the array, but this array is creating inside this constructor. So if you assign, first of all, you assign this array, and after that, you, for example, in the loop for example, to 10, you put some of the elements to that array. This is something tricky in the JVM, because the second thread which reads that field might see the empty array. Because from the JVM perspective, there's not guaranteed that the value of this array will be shared. But if you move that computation a little bit in the different order, so first of all, you allocate the local variable, put the loop, and after that you assign to the field, that will be visible to another thread. So that is the guarantee from the Java memory perspective. And basically the sequential consistency seems like this. So we have on the left, we have a one thread, on the right, we have a second thread, and this is the kata tools. So basically, yeah, that might be potential result. So we can see that we have a x0 and x0, x1. So basically, that might be the different results. So this is not basically Java is not strong consistency, and you need to be aware that whatever you assign to the, even for the volatile field, is not strictly consistent. So basically, it's not automatically flashed to memory. And yeah, so basically I mentioned about happens before. So happens before is a relation which a little bit difficult to explain, but you can, for example, I have basically two natural examples. So first of all is where you want to, for example, drink tea. First of all, you need to, for example, take the cup. After that, you need to pour the water and put the tea. There's the sum of the ordering. And basically, with the happens before is pretty much the same. So you need to think in the concurrence application how potentially that code will be written by the CPU, and you need to provide some of the synchronization. The second example is, for example, library. So if you take some of the book, but you have for example, library card where you put information that particular book was taken by the Krystian, for example. Without that card, everyone can go to the library and try to accessing this book, but the book doesn't exist there because someone is already, the book has been already took it. So that is a little bit different, that is a little bit difficult to understand that relation, but but most important part of the happens before is ordering, how basically we want to read from the volatile. And if there is a couple of points on the in the JVM, where, for example, having synchronize, we going to the we going to the synchronize method and we exiting from that particular method. That is happens before relationship. Where we, for example, calling the thread start. This is also volatile only write is happens before read. Basically, we cannot be sure, and the couple of different methods, like for example, read and lock also is happens before. This is that academic posture about the happens before, like the transaction closure. So basically describe the relation, how we need to order our program and synchronize to achieve that this happens before. We don't have enough time to explain it, but it's very interesting. And also we need to thinking about the consensus and the causality. So in the JVM, where we have multiple access to the single source of truth, so collection or database, we can say about the consensus. So there's nothing in the JVM which can say, okay, we have 8 threads which accessing that particular map or list, and we can make some of the consensus that we see some of the proper state. Everyone. It's not true. Basically, every thread can see totally different results, and that is mostly related with the causality, because where we're working with the multi-core architecture, every core can make it that in the different way, make it the different optimization. Even your thread can have a different code optimized by the, for example, JIT compiler. One thread can read the code as interpreted, but the second can read already compiled code by the JIT compiler. So this is the totally different, and accessing for state of the source is also dependent on that. And pretty much how we can explain it. So this is the sum of the explanation. So we have a causality where A is before B. It had to be happened before B. So that is guaranteed by the happens before the program order. This is called in the JVM as a temporal relation. And consensus is basically where the multiple threads try to reach one common decision. So this is a little bit difficult. This is the boring presentation, I guess. So most of the time where we're writing concurrent programs, we don't care about the Java memory model, because we're using the Lego from the Java util concurrent, and pretty much everything is simple. But I think we have in our industry, we have we have a couple of myths, like the machines do what I tell them to do. It basically not true, because the whole computation, especially in the JVM and modern CPUs, this is the illusion of execution. We don't have any idea what instruction, we don't have any idea about the ordering of the instruction. We don't have any idea how basically the data are shared between threads and so on. And our naive mental model is basically is that everything what I write to the heap is serialized to main memory. But it's also not true, because CPU and basically our hardware is asynchronous by default, and in the middle of the CPU and memory we have caches, we have messy protocols, coherence protocols, and so on. So there's a lot of things what can happen between flashing to main memory, which doesn't guarantee consistency. And you can say, okay, so total store order machines, like for example, architecture 86, can protect us. And this is true, and but only in the 99%, because this architecture is strong enough to basically cover common cases. But if you, for example, work with the ARM or PowerPC, which is, I think, common pattern currently in the cloud, it's not enough. So explicitly, you need to add additional synchronization. And after presentation, we can talk about how we can test it by the JC stress, and I can show you a couple of the examples how basically the difference are between the 86 and ARM. And yeah, we can say, okay, so if the concurrency is very bad, so maybe we can say about the single thread. And yeah, this is some of the solution, because there's something like the thread per core architecture. So we have a single thread which is pinned to the proper core. This is so imagine that this thread is on the core 1, this is on the core 2, and we have different data stores, and we're trying to process that. Of course, in some of the level, we need to share this data. So basically, we have also strategy for that, like the shared nothing or different techniques. But these projects basically rely on that. Of course, in the JVM, we have our own library, which also rely on the thread per core architecture. Currently, Cassandra is also under rewriting to the thread per core, Kafka also. So we can say the single thread wins. And yes, we can say that the single thread wins only from some of the perspective. But from my perspective, the concurrency is not the tool. It's just the tool, not the religion. So we can use it concurrency where we need it, and mostly of time we don't need it. Of course, where we have some of the API and using the HTTP server, this is the default. But concurrency is also investment. Currently, for example, your system is using by the 10,000 clients. But what if we are in the 5 years, we have 10 millions of users? So this is the totally different situation, and we need to thinking a little bit earlier on that. Checklist, we need to somehow decide between the concurrency and parallelism. So if you have a mostly I/O, you need to consider asynchronous concurrency, or if not, you try to optimize synchronous flow first. If your task can be decomposable, so you need to consider the forging pool, which basically is on the JVM right now, on the Java, sorry, or try to using the batching or single thread per task, but it's not recommended. If you block on the I/O, you need to consider also or maybe non-blocking APIs or virtual threads from the project Loom, because are fitable for that, or fixed thread pool and try to manage that. If you're creating a lot of tasks, of course, the queues or virtual threads are enough, or maybe pooling. If your performance is worse, where you're providing and increasing more threads, you need to revisit the synchronization points and the context switching, because that might be very expensive. And where you decide to increase the number of the thread in your application, previously you measure what is your performance, what is your metrics, and after that try to prove it. And you need to be also aware that the concurrency is not the powder for the bad architecture decision. So if you decide to go to microservices and you have a huge traffic between two components, number of the threads and the concurrency sometimes is not enough. But also I want to share somehow about the Kafka streams, because Kafka streams has a different approach. So basically, each thread on the Kafka streams can execute one or more stream threads, which basically this is the unit for the processing Kafka topologies. And you can see that sometimes applying the different techniques and the different approaches for resolving such of the issues, still you can use the number of threads like your CPU number, CPU core number, and you can handle a lot of traffic. So this is pretty much from their documentation. So I think the concurrency should be not by default, should be basically under the discussion and trying to put where is proper place for it. But you potentially also read it or hear it about the avoid the premature optimization. But I disagree a little bit with that, because if you try to think about the concurrency at the beginning of your greenfield or new project or something like that, sometimes it's the root of the success, because you can use a very short number of the threads and achieve even better performance. So don't use the concurrency without factual justification. Of course, this is not applying for the HTTP, because by default in the Java, every request is assigned to the different thread. Of course, where we're trying to measure in the millisecond or throughput, this is the good option, and where your bottleneck can be proved. And of course, the complexity is for the ROI. So it's okay. And from my perspective, think a little bit harder and should be fine. But don't optimize by the imagination, only by the metrics, because I think more threads, sometimes it's not faster. JVM is hard, but if you don't write the libraries for example, log-free structure and write or something like that, you don't need it understand of the Java memory model. You need to just understand the Lego and minimal understanding of the happens before relation. But what is more important, if you go to that particular package, every method, for example, in the Java concurrent hash map or concurrent link queue, every method is described that method provides happens before or not. It's phrase safe or not. So basically, the annotation on the Java doc is very helpful during the implementation. And this is only from my perspective. If you want to more this information and more knowledge about it, you can follow me on the LinkedIn, because I'm sharing some of the stories from my battlefield. So thank you very much. That's it from my side. And if you have any questions, I will answer on that.
Who would like to start with a question?
Do you plan to make more detailed conference or presentation later, maybe in the future?
Yeah.
Okay.
Yeah. So basically, I have a extended version of this with the JC stress example, but yeah, we don't have enough time. I can show you on after the presentation, so we can discuss after. So of course, if you are interested in that topic, I can be here again. So.
More thoughts?
Thank you. I have a question. You mentioned that when we use a cloud, we don't know what the architecture of the processors. And do you recall any big failures maybe in other companies when it happened that the code was not CPU architecture agnostic and it tended to some problems?
Yeah, so basically mostly of time where we using the Java concurrent, Java util concurrent, the implementation of the JVM is written for the different architecture, CPU architecture. So, so this is provided by the JVM by default. But what is more important, some of the implementations are default. So basically, the JVM is written in that way. Every method and every structure on the JVM, which is written in the C++, has a default. And that default, imagine that new CPU architecture arrive on the market. So JVM will be run on that CPU architecture and will be working very well, but without the performance optimizations. Mostly of time, of course, we use previously the 86, which is, I think in the 99% is the optimized specially for it. So I can show you one example from my Battlefield. I have an application where we accessing data from the native memory. And on the 86 architecture was faster with the volatile comparing to the acquire release. This is the different barrier, but from the memory accessing, the release acquire is the not strong enough, which doesn't mean also it's faster comparing to the volatile. But guys from the Oracle provides more optimization for the JIT compiler, and it was faster for the volatile comparing to the release acquire. And what is more important, such of the techniques are also different on the ARM, because where we're talking about the synchronize is enough, because synchronize is proven and guaranteed that this is the behavior is the same. But for example, atomics on the ARM are faster comparing to the 86. And people basically, companies going to the cloud because it's faster, but in some of the circumstances, accessing for the different native memory atomics might be a different behavior. So what I mentioned, the atomic long is faster on the ARM, but in some of the circumstances, it might be slower, for example, for the atomic integer. But it's not for the single integer and get, because this is the comparing and swap. But for example, if you have a weak compare, right? This is the totally different performance expectations. Of course, we don't have a time, I guess. But yeah, basically, you need to be aware that if you writing something, running something on the ARM, for example, on the Google AWS, it doesn't matter. You need to be aware that your machine should be pretty much similar. I'm not talking about the clock, CPU clock, but on the architecture perspective. Because if my Mac, for example, is the ARM, and I deploy to the, for example, Graviton on AWS, I can be pretty much sure that the result will be the same. But where I'm working on the Windows and I'm using the 86 and deploy to Graviton, the synchronization point might be the different. So, for example, even correctness of the application will be different. So potentially, but this is not the case every time. So you need to check it. And from my perspective, where you using the different version of the JDK is also the difference. So yeah, that is very near to hardware, and I think most of the time we don't care about it. But yeah, there is the difference. So we need to be aware about it. Yeah, we can discuss later, I guess, because we don't have a time.
We have time for one more question.
Okay.
I would like to ask if you have any data comparing Java with C or C++ language, how many threads you can run in Java and in C++, for example?
Yeah, so comparing depends on the context, because where we're using, for example, new project Panama and using foreign memory functions and accessing the native memory, the performance will be similar. I have experience with Rust where we gaining the twice faster. The application was twice faster comparing to the Rust. Rust is fine, but where you're using the Java and, for example, Java foreign function and you accessing the native memory, the allocator and JIT compiler can produce much efficient code that comparing to the to LLVM. So depends on the context. Might be faster, but the problem with the Java is allocation, where your allocation rate is very high. You can spend a lot of time on the accessing to the memory. So that is the problem. And yeah, I can say that the Java is faster to C++ because that depends on the context. But mostly of time you can reach the same performance and even achieve the same hardware requirements comparing to the C++.
And it depends from a processor, for example, or not?
Yes. Potentially, yes, but I can say that mostly of time is depend on the what version of the JVM you run and which version. Because comparing to the Corretto, if you deploying to AWS, the OpenJDK is much slower comparing to the Corretto version of the JDK. Why? Because people from the Corretto, from the Amazon, provide some of the optimization for the gravitons, for example, and this is much faster. Of course, after all, they trying to merge it to the OpenJDK, but it's taking a lot of time to approve it and so on. So yeah, that is the situation.
Please welcome on the stage Paweł Niewęgłowski, who will present the award.
Thank you.